So damping in simple harmonic motion. So you need to be able to know the effects of damping, including these terms underdamping, critical damping, and overdamping. Damping in simple harmonic motion, as you can see from this graph here, here's the amplitude, the y displacement, and the amplitude gets less and less over time as the oscillation continues. And this shape, this what's called the envelope, or the pattern of the maximum amplitude, the amplitude decreases in an exponential curve. Damping is caused by friction or any other loss of energy to heat or similar, and in this case we've got the trace of a piano note, and this is with the sustain pedal so that you can actually have the note stay for longer, and that's reducing the damping of the piano string. We've got this simulation, which if you click on this, it'll take you to this, which can be a full screen. And here you can put on and off these weights. So if I click a weight on there and then start that, then you'll get a plot here of the velocity and the displacement. The other thing you can do is have a second spring. So I'll put one on that's undamped and another on over here which is damped, and you can see the two shapes are quite different for the two springs there. So you can play around with that yourself there for that one. Going back to what we were talking about before. So there are three types of damping that you need to know about. The first one is underdamped motion. That is what we've just really been looking at. There's something continues to oscillate, so it keeps going up and down, but the amount of energy that's taken out of the system is progressively less and less, and so you end up with that kind of classic damped simple harmonic motion. If something's overdamped, then there's too much friction. It never actually reaches the equilibrium point. It just slowly creeps towards it and then probably bottoms out here, and it never actually reaches the equilibrium point. Something which is critically damped has got just enough damping to reach the equilibrium but doesn't overshoot and doesn't actually oscillate. So there's just the right amount of friction there to achieve critical damping. That's the kind of damping which is achieved in a car shock absorber, where you've got the friction in the piston that's in there, and you can watch that video later. Same thing in mountain bike, forks and suspension systems, where you've got maybe an air chamber, but then you've also got baffles to provide a bit of resistance to make sure that you don't bounce around. I'm going to finish off with a video of a car where the dampers have been removed and the driver has intentionally braked so that the car starts to bounce around, and you can see it go again here. So as soon as he brakes, there's a lot of bounce, and he's promoting that bounce. Please don't try this at home or on the road, because they've actually removed the shock absorbers to make that happen. So a lot of things in engineering require critical damping to make sure that things do oscillate correctly, or quite often we don't want things to be oscillating.